Okay, so the next example is a very famous, very important power series. It is the sum n goes from 0 to infinity, x to the n over n factorial. Okay, so we're asked to find the radius and interval of convergence of this power series. So, as before, let's just define L. This will be the limit as n goes to infinity of the absolute value of an plus 1 over an, where the an's are the whole terms, so we include the x's. So this is just going to be x to the n plus 1 over n plus 1 factorial times flip an upside down, n factorial over x to the n equals lim n goes to infinity. Now let's see what cancellations we get. Well, the x to the n is going to cancel with the x to the n plus 1 up top. And now we need to see how the factorials cancel. But remember what was factorial defined to be. So n factorial is n times n minus 1 times all the way down to 1. So then n plus 1 factorial is n plus 1 times n minus 1 all the way down to 1. Okay, so most of these terms, except for 1, cancel. The 1's cancel, the n minus 1's cancel, n's cancel. And we're just left with the n plus 1 on the bottom. So we get lim, n goes to infinity, x over n plus 1 in absolute values. Okay, but for any fixed x, this is equal to 0, which is always less than 1. This is for all x element of R. So no matter what x we plug in, we get by the ratio test that this series converges. So hence, R equals infinity, and the interval of convergence is the entire real line. Okay, let's move on to the second part, this important result. So, as for all x, this series converges by the first part. We have by the divergence test, so by the divergence test, that the terms have to go to 0. So it says that the limit as n goes to infinity of x to the n over n factorial has to go to 0 for all x, which implies that the limit of the absolute values of these terms goes to 0, because if they go to 0, then their absolute values go to 0. Okay, so the next part asks us to use L'Hopital's rule to show that for any given value of x, this limit identity is true. So first I'm going to define am to be the object we're limiting, so 1 plus x over m to the power of m. And we'll find that if we define cm to be the natural log of am, which is equal to ln of 1 plus x over m to the power of m. Using the law of logs, I can bring down that m. Ln 1 plus x over m. And now, using an algebra trick, I'm going to write the m out front as dividing by 1 over m. And I'll find that limiting this is going to be easier. So let's take the limit as m goes to infinity of cm. This is equal to lim m goes to infinity of ln 1 plus x over m over 1 over m. both top and bottom go to 0, and that's why I've written it in this form, so I can use L'Hopital. Equals lim, m goes to infinity, differentiate the top with respect to m. You're considering m now to be a real variable rather than going through the natural numbers, but the function still makes sense for real m, positive real m. So if we differentiate the top, we get this, and if we differentiate the bottom, we'll get minus 1 over m squared. So we're going to get this cancellation. The minus x over m squared will cancel with the minus 1 over m squared, and we'll just be left with x on the top. So this is lim m goes to infinity, x over 1 plus x over m. Now, if we limit m to infinity, that 1 over 1 plus x over m is just going to go to 1. So we'll get x over 1 is just x. Now, how can I use this to establish the equality I was asked for? Well, I can say, so hence, lim m goes to infinity. Now I'm going to limit am. So 1 plus x over m to the m is equal to lim m goes to infinity. I call that am. Now if cm was ln am, then am is e to the cm. Now, using continuity, I can bring that limit up to the top, and this is going to be e to the limit as m goes to infinity of cm, which is e to the x. Okay, so we've established the equality that we were asked for. Okay, so if you're following the printed version of the notes, I'm going to change part 2 slightly to verify by using the binomial theorem. Is that the following equation holds: 1 plus x over m to the m is equal to sum k goes from 0 to m of m factorial over m minus k factorial times 1 over m to the k times x to the k over k factorial. Okay, so this amounts to literally just plugging into the binomial theorem. There's not much else involved. So here our a is 1 and our b is x over m, so using the binomial theorem, this is equal to, by definition of the binomial theorem, or by the equation we get from the binomial theorem, m choose k, 1 to the m minus k, x over m to the k, the 1 to the m minus k just turns to 1, so we ignore it. Expressing m choose k in terms of factorials, we get this, x to the k over m to the k again goes from 0 to m. Then grouping everything just so it looks like how we want it to look. K equals 0 up to m factorial over m minus k factorial, m to the k times x to the k over k factorial. And we're done. Okay, now on to part 3. The part 2 and 3 that I have here are equivalent to what is in the notes. They're just written in slightly different forms. So verify that the limit as m goes to infinity of this object m factorial over m minus k factorial m to the power of k equals 1 for all 0 less than or equal to k less than or equal to m. Okay, solution. So this just involves, the hard part about this is just recognizing how the factorials cancel. So then m goes to infinity, m minus k factorial, m to the k under m factorial equals the limit. Now let's write out m factorial. That'll be m times m minus 1 times dot 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 m minus k minus 1 times m minus k, assuming again that k is less than or equal to m, dot 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 1 all divided by m minus k factorial. Now remember, if k is equal to m, then this is just 0 factorial, so we're fine, because 0 factorial is 1. Now we see that this piece that I've highlighted is m minus k factorial. So this piece cancels with the m minus k factorial that we have in the bottom. And we're just left with lim, m goes to infinity, and now it looks like the part 3 that's in the typed notes. So all the way down to m minus k minus 1 all over m to the k, which is just m times itself, k times. And the thing to notice now is that there are k things on the top and k things on the bottom. So k terms and k terms. So divide each m on the bottom into one of the factors individually. So divide the first m on the bottom into the first m on the top, we just get 1. Divide the m on the bottom into the m minus 1, and we get 1 minus 1 over m, all the way down to 1 minus k minus 1 over m. And each one of these individually limits to 1, so the product limits to 1. And we get exactly what we were asked to prove. Now let's group all this information together, part 1, 2, and 3, to solve part 4. So in part 1, we showed that e to the x was equal to this limit, which we expanded using the binomial theorem. In part 2, to give us this limit, m factorial over m minus k factorial m to the k times x to the k over k factorial. Now this is equal to, well, we can just change the sum to an infinite sum. K goes from 0 to infinity, and limit what's inside. Now this is not an obvious fact, but it is true that we can just extend the limit at the sum at the start going from 0 to infinity, and we preserve the equality. Again, this is not obvious, but it is true. This is equal to, by part 3, that limit I have in brackets is just 1. So this is k goes from 0 to infinity, 1 times x to the k over k factorial, which is just equal to sum k equals 0 to infinity, x to the k over k factorial. Okay, so we've established the equality that we want. Now this is a very famous equality. The x is equal to this power series representation, and as we showed in part A, the radius of convergence of this power series is infinite. So E can be expanded on all of R in this power series.